like 2, 5, 3, 6. And I wanted to find A inverse. The first thing that I need to do is to find the determinant of A. Now, because this formula includes 1 divided by the determinant, whenever that determinant of A is equal to 0, we actually say that the matrix is not invertible because we can't divide by 0. So the first thing I'm going to do is to check. So I'm going to find A inverse. I'm going to check for the determinant of A. So our determinant is equal to whoosh, minus whoosh. Sound effects are important, people. 2 times 6 minus 5 times 3. Once again, whoosh, minus whoosh. Okay, so 2 times 6, I've got 12 minus 15. So that's -3, which is fine. It just can't be 0. So our determinant is -3, and now we can go about finding and writing down what our A inverse is. So A inverse will be equal to 1 divided by -3 times, and now we're going to follow this formula. So I'm going to swap the diagonals. So I'm going to swap the 2 and the 6. And then I'm going to make the off diagonals negative. So -5, -3. And my last step is going to be to distribute in that -1/3. So when I distribute that in, it's going to be multiplied. I'm going to take each entry in the matrix and multiply it by the -1/3. So 6 divided by -1/3 is going to leave me with -2. -5 divided by -3 will just make that a positive 5/3. -3 divided by -3 would be a 1. And then I'll have -2 divided by 3. Say that I had an equation, a matrix equation or a vector equation that looked like A times X is equal to B. And what I mean by that is 2, 5, 3, 6 times the column vector X, Y is equal to some other numbers. Let's say B was 1, 5. Well, this right here, if I do the matrix multiplication on the left-hand side, this would say 2x plus 5y and 3x plus 6y. And that has to equal 1, 5. So this system of 2 linear equations, something we've been working with for many years. We've got lots of different ways to solve this. We can solve it graphically. We can solve it with substitution. We can solve it with elimination. We've got lots of options here. If we take this system of equations and write it in matrix form, we have a new option to solve it. So if I start with that idea of this equation has the form AX equals B, if I wanted to solve for X and A and B were numbers, we know we just divide by A. Since A is a matrix, instead of using division, I'm going to multiply by the inverse. The order that you multiply things in matters when we're talking about matrices, so it's important to note that I'm multiplying by the inverse on the left-hand side. If you tried to multiply on the right-hand side over here, the dimensions wouldn't work out and you wouldn't actually be able to do the multiplication. Here, if we were solving this system would mean finding X and Y values or finding the vector X. Well, we're going to get that vector X over here because A inverse times A is the identity matrix, and multiplying by the identity matrix is like multiplying by 1. So this simplifies to say our x vector is equal to A inverse times that B vector. So if I wanted to solve this system of equations, I know that my answer would look like xy is equal to A inverse -2 5/3 1 -2/3 times our B vector 1 5. Now the result might not be pretty, but using our matrix multiplication we can get it. So this is a 2 by 2. This is a 2 by 1. My inner dimensions match, and the outside tells me the answer should be a 2 by 1. So to get row 1, column 1, row 1 times column 1, I'd have -2 plus 25/3. I don't know what that is. I'm just going to leave it alone. Here, to get my y component, I'd have 2 plus -10/3, or 2 minus 10/3. And that should be the solution to this system of equations.